So essentially this is the same as the experiment that we've just done. The ball has a mass of 0.05 kilograms and is dropped vertically from rest through a height of 1.6 meters. So the ball is being dropped from up here down onto here, and there will be some kind of time of contact upon the impact here, and that computer is going to measure that along with the force that is applied here. So it's a slightly more advanced version of the experiment that we did. So the computer comes out with this graph here. The graph shows how the force in the ball varies with time during the impact. Show by calculation that the magnitude of the impulse on the ball is 0.35 Newton seconds. So how can we calculate impulse from what information is given? We don't have force and time given as quantities, but we do have this graph, and impulse is equal to the area under that graph, exactly. So impulse is equal to the area under that force time graph. It's effectively just like multiplying force by time. So that's going to be a half times 0.01 because that's milliseconds here times 70. That will give you 0.7, and then you can just divide that by 2. That's effectively the same as calculating the area of this and this together. 0.35 Newton seconds. You could have done a half times 70 times 8 plus a half times 70 times 2, all times 10 to the negative 3. And that would have given you 0.28 for this bit and 0.07 for this bit. Add them together and you'll get 0.35 Newton seconds. So that's part 1 done. Part 2. What is the magnitude and direction of the change in momentum of the ball? Well, what do we know about impulse and change in momentum? They're the same thing. Yeah. Ft is equal to mv minus mu. Ft we've just calculated as being 0.35, so 0.35 is equal to mv minus mu. So we know that momentum is 0.35, but it's also asking for the direction as well, so you'll only get half a mark for given 0.35 kilogram meters per second. In what direction is the change of momentum going to be? Anyone? Shout it out. Not down the way, up the way. Vertically or upwards, yeah. There is no real indication here of, how the vector should be stated, so you would be able to accept anything here. So upwards, opposite direction, north, 180 degrees to its original direction, anything like that would get you your extra half mark there. But you'll only get 1 mark for this bit, because remember it asks for direction as well. Part 3. The ball is travelling at 5.6 meters per second just before it hits the force sensor. Calculate the speed of the ball just as it leaves the force sensor. So we're going to have to use impulse being equal to change of momentum again. Impulse we know as being 0.35. The mass of the object is given as 0.05 kilograms. So 0.05. We're looking for the speed at which it's leaving this at, which is v, minus 0.05 times 5.6. Now that 5.6 is its initial speed just before it hits the force sensor. So travelling downwards, you could take it as negative, you could take it travelling upwards as being negative. It doesn't really matter, remember, as long as they've got opposite signs so that they indicate that they're going in opposite direction. What I would do here is make it going downwards as being negative, just so we end up with a nice positive answer. So I would take this as minus 5.6, because remember it's velocity, it's got to take into account the direction that it's going in, so you end up with negative 5.6. Figure all that out and you'll get V as being 1.4 meters per second. Now part B, it's a bit more difficult. Have a read through that just now. Another ball of identical size and mass, so it's the same mass but it's made of a harder material, so we can think back to the experiment where we had snooker ball versus maybe bouncy ball. It's dropped from rest and from the same height onto the same force sensor, so everything else is the same. The only thing that has changed is what the ball is made of. Sketch the force time graph shown above, and on the same axis sketch another graph to show how the force on the harder ball varies with time. You don't need to give numerical values, but you must label the axis correctly. So the first thing you've got to do is sketch out that force time graph. So this is force, this is time, and then it looks something like that. That's pretty much it here, I think. So that's 10 and this is 8. So there are really two things that you need to indicate on this graph. It's a harder ball, so is the force going to be larger or smaller? It's going to be a larger force. And think about the snooker ball and think about the bouncy ball. Is the time of contact going to be more or less? It's going to be less. So what you're looking to draw on here is a greater force. So I would say maybe something that goes up to about here, but it's got to be in less time as well. So as long as that comes down here before that 10 milliseconds along the bottom, then that would be fine. So something that's made of a harder material will have a shorter time of contact, but will have a larger force.